I'm going to fill the sites in. So I have 4 single bonds and 1 lone pair. Where should I put the lone pair? In an axial or in an equatorial? Does the lone pair require more space or less space than a single bond? It requires more space. So I want to make sure I put the lone pair in the site with the most space. The site with the most space would be axial or equatorial? Equatorial. And so what we do is, I'm going to pick this equatorial position to the right here, and then I'm going to put the fluorines in the axial up here, and the one down here, and then 2 of the fluorines I'm going to put in equatorial, here and here. Do you see that? For this. Can you build this? Uh-huh. Is that the brown ball? You have to use the brown one in the middle. Yeah, okay. Just put 5 sticks in there. That looks okay. Just go ahead and build this. The silver one's for the next one. We're just going to use this one for right now. So we see the EG here. Let's look at the angles over here. The axial equatorial angle here is 90 degrees. The axial angle is 180 degrees. And the equatorial angle is 120 degrees. So we have 3 angles in this. A 90, a 180, and 120. Do you see all 3 angles in the structure? So the EG is trigonal bipyramidal. But the MG is not. We don't see the lone pair. So how would you describe this shape here of just the bonded atoms? How most people describe the shape is they tilt this 90 here, and then they have the 2 fluorines here form the legs of a seesaw. And then the axials will form the plank of the seesaw. And so the MG is called seesaw because it resembles a playground seesaw. Now, what are we going to do about the orbitals? Because if I look at sulfur, sulfur is 3s, 3p. And how many electrons does sulfur have in this structure? So let's count them. It has 1, 2, 3, 4, 5, 6. So it has 0 formal charge. And so it's going to have 1 lone pair, and then 1, 2, 3, 4, actually 1, 2, 3, 4, 5, 6. When I look at this, it doesn't look like it can form more than 2 bonds, right? And so then the next orbital would be 4s and then 3d up here. So what we're going to do is we're going to completely skip the 4s. And we're going to, oops, sorry. We're going to completely skip this and hybridize these. And so if we were hybridizing those, what we're going to get is we're going to get 5 orbitals each of these is an sp3d orbital. And so we're going to have one lone pair and 4 singles. This is going to be for sulfur. And then what can happen is fluorine can come in and bond to this. So fluorine comes in here, bonds an sp3. These would be sp3 fluorines. And so it's going to look like this. I have an sp3d axial, sp3d equatorial, sp3d axial, sp3d equatorial sticking out, and sp3d equatorial sticking in. To this, I'm going to add a lone pair here in the equatorial, and then I'm going to fill these other ones with a single electron. And that way, fluorine can come in here and bond. Fluorine's orbitals are quite small. This is going to be an sp3 here. Do a spin down. And then it's going to have another sp3 coming out, lone pair here. An sp3 coming out, lone pair here. sp3 going in, lone pair here. 3 lone pairs. So I'll have a fluorine there, fluorine here, 2 in the plane, 1 sticking out, 1 going in for tetrahedral. Getting messy, so this one I'm not going to draw so accurately, like that. So this would be the valence bond picture here for this. Now, this only happens for larger atoms, and they have to have d orbitals. So this only happens for 3rd shell and up. This can't happen for 2nd shell. 2nd shell lacks 2d orbitals. Those are forbidden. Therefore, 3rd shell and higher. So we have some other molecules that we'll look at here. I'm sorry?
Isn't there 4 fluorine?
Yeah.
I only see 3 diagrams.
Oh, here? You mean this diagram?
Yeah.
This one I didn't draw so clearly, but this one's stuck in the back.
That's a fluorine.
This is a fluorine here that's stuck in the back.
Is it like, I don't even know how to think of it.
It's supposed to be tetrahedral.
So it's not even on that other end there?
It's attached to this. Do you see this dotted one here?
Kinda. Yeah.
This is sp3d equatorial. So that's,
Oh, that's not. Okay.
there are 5 sp3. There are 3 equatorial ones. Uh-huh. If we show it in 3-dimensional, you could try to show the this with the lone pairs. You know, here it could be more forgiven. So 1 lone pair in the plane, 1 lone pair sticking out, and 1 lone pair going in. You know, you could show it like that if you want 3-dimensional Lewis structure. But most people, they don't. It gets too complicated maybe for, or hard to follow? Uh-huh.
On the top fluorine, why are the SPs different? SP are on the diagram behind you. On the top fluorine, the orbitals.
These?
The SP, yeah, like where it's in SP2, SP3, SP.
Oh, because I didn't write these properly. They're all SP3s. So it'd be something like this. I'm trying to show it. All right, pluck off, all right, what we're gonna do is we're gonna build another one that's gonna be easy to build. So don't take apart your SF4. We're going to PCl5 next.
Quick question. So the fluorine at the very top, like the bottom one, is that an SP3 or a 2?
All these are SP3, fluorine's SP3.
Okay.
If we do PCl5, we do the Lewis structure, it's going to come out like this. We have 5 chlorines bonded. There are no lone pairs on phosphorus. Chlorine doesn't like the bridge. So this one is going to have an EG that's going to be trigonal pyramidal and an MG that's trigonal pyramidal. We can label the chlorines axial and equatorial here. This turns out to be non-polar because this is going to have spherical symmetry. And so what happens is it's equal and opposite poles. The chlorine's more electronegative, but they all cancel. And so this axial cancels this axial, and the equatorials cancel. And so this is a non-polar molecule. Even though it has polar bonds, the bond dipoles add up to 0. And the angles are undistorted. So if we're looking at chlorine axial, phosphorus, chlorine axial, the angle is 180 degrees. If we're looking at chlorine axial, actually, let's just keep it simple. Axial to equatorial, that's going to be 90 degrees. And then equatorial to equatorial, the angle is going to be 90 degrees here. Whereas over here, the angles are going to be distorted because of the lone pair. Since I have that lone pair, the axial is going to get pushed to the left, and this axial is going to get pushed to the left. And the angle is going to be the shortest, not the widest. So this is going to widen out to more than 180, but this is going to shorten. And so what we see here is going to be axial to axial should be 180 degrees, but we're going to guesstimate 178 degrees. This is the lone pair. And then we have axial to equatorial, should be 90 degrees. But maybe it's going to go to 88. And then we have equatorial to equatorial. This one should be 120 degrees, but we're going to distort it. And so this is going to be distorted similar to what we saw for the other one, 116 degrees. And so this is going to be a distorted seesaw. It's not going to be a perfect seesaw because this pushing in these. The next molecule we're going to look at is ClF3. Chlorine has 7 electrons. 3 fluorines would be 21 electrons. So this is going to give us 28 electrons. Now, chlorine hates to be in the center, so the only choice we have is put a fluorine on the terminals here. And then complete the octets to the fluorine. And that takes care of 3 times 8 is 24 electrons. And so we have more electrons left over, 26, 28. So that gives us 2 lone pairs. Now we have 5 groups. If we have 5 groups, it's going to be trigonal bipyramidal. And so I'll stick the chlorine in the center. And then I have to figure out where I want the lone pairs. Where do you want the lone pairs? In the axial or the equatorial? In the equatorial. And so one equatorial sticks out like this, the other equatorial sticks in here. And then I'm going to put 1 fluorine in the equatorial over here, and then 2 fluorines in the axials, here and here. So can you build this one? Did you check one of these out? This is a participation lab, so you're going to have to make it up if you want the points for this one. So get the structures from somebody else that we already did and build those.
Wouldn't have 27 electrons?
27?
Yeah, because one fluorine has 9 electrons.
No, fluorine has 7 valence electrons, and we have 3 of them, so 3 times 7, sorry, what is 3 times 7? 21, right? Plus the 7 from the chlorine, and gives us 28 electrons. So the EG on this is what we call trigonal bipyramidal, trig bip. And then the MG, what would you describe the molecular geometry of this to be? Just look at the bonded atoms.
Trigonal planar?
Trigonal planar is what you get if you put the 3 fluorines in the equatorial, and then the lone pair in the axial, and the lone pair in the axial. Then you'll get trigonal planar. But the axial is not the best position for the lone pair. The best position for the lone pairs is equatorial. Why? Because there's less repulsions. So make sure you put the lone pairs, the 2 of them, in the equatorial, and then fill in the rest. So you need 2 sticks in the equatorial.
That's an EQ, right?
I'm sorry?
That's an EQ.
Yeah. This is equatorial, 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 axial, axial. And how would you describe the shape? The shape is called T-shape. Can you see why it's called T-shape? But it's a distorted T. Because the axial to axial angle should be 180. It's going to be less than 180. We got these 2 lone pairs here. We're not going to get too fancy. So we're going to look at the axial to axial. Axial to axial is ideal is 180, but it should be a little bit less than 180. And then we have the axial to equatorial, which should be 90, but it's going to be less than 90. Distortions. And so it's going to be a distorted T, what we call distorted T. Noble gases are very unreactive, but fluorine is quite reactive. So sometimes you can get a noble gas, a big one. Helium never reacts. Helium is small. But if you go to the big, what's one of the biggest noble gases? Xenon. Radon's bigger, but radon's radioactive. And so it turned out that somebody actually made a noble gas compound, XeF3. It doesn't last for very long. This is unstable. But we might want to know what the shape is. And so xenon has an octet of 8 electrons. which is weird. 3 fluorines is going to give us 21 electrons here. And how many is that? Actually, I did this wrong, sorry. It's XEF2. I don't want XEF3. XEF2. 2 fluorines, which is 2 times 7 is 14. So that gives us 22 electrons. And so we'll throw a xenon in the center. And then we'll put a fluorine up here. The fluorine down here, complete their octet, and we've used 16 electrons. Use 16 of the 22 electrons, we'll have 18, 20, 22 electrons. So we need 3 lone pairs. And that means there are 5 groups. If there are 5 groups, then we call that trigonal bipyramidal. And where do the electrons go? In the axial or the equatorial position? Equatorial. And so this is linear, is the Mg. The Eg is trigonal bipyramidal, and the angle here is 180. It won't be distorted. This one? This one because if you have 2 lone pairs, then we expect, let's say, a 4-degree distortion, but the 4-degree distortion might be too extreme for this. We can go ahead and do that. So if we do it a 4-degree on the 180, it would be 176, about 176. But then what do we do about the 90? If we do the 90 and go down to 86, and then we have an 86 here, then 86 plus 86 gives us a 172 angle. And so it doesn't quite work out in this case, so that's why I just fudged it. Because if we did a 4-degree for the 90, that's 86, a 4-degree for this 90 is 86, but then the 180 is a 4-degree distortion, that gives us 176. It doesn't add up. Do you see that? So since this one doesn't add up, it's somewhere in between. So that's why I said that. You could make it add up, but then what do you do? Maybe a less than a 4-degree distortion here and more than a 4-degree distortion there, or what do you do? And so the best thing is we would analyze this using quantum mechanics, and quantum mechanics will give us the bond angles here. Or we do it experimentally and see what the experimental bond angles are. Okay, since we have the model kits, we'll continue on. All right, so when we have trigonal bipyramidal, we have the molecular geometries that we can observe are trigonal bipyramidal, seesaw, T, and linear. And so when we have trigonal bipyramidal, EG, we have 4 different MGs that we can have depending on how many lone pairs there are. This is all in the table in the book, so if you take a look at the book, it's pretty well sorted there. When we have 6 groups, so the next example is going to be SF6. We have 6 groups there. So we have sulfur with 6 electrons, and then we have 6 fluorines, 6 times 7. 42. And then that gives us a total of 48 electrons. Fluorine never goes in the center of anything, so what we're going to do is we're going to stick 6 fluorines on the sulfur. And that's way more than an octet. An octet is 8. This is 12. 2, 4, 6, 8, 10, 12. And then we use the rest of the electrons to complete the octet to the fluorines. And so we need another orbital to accommodate the 2 extra electrons from the previous. And so the way to do this is we're going to take a 3s and the 3 p's here, and then the 3 d's out here. The 4s are going to be completely skipped because the 3, they're not part of the 4 is not part of the n equals 3 family of orbitals here. And what we're going to do is we're going to hybridize 2 of the d's. This. And so what we end up with is 6 orbitals called sp3d2. When we hybridize those orbitals, they're going to be in what we call an octahedral arrangement. There are 2 ways of drawing an octahedral arrangement. One is like this. Where each of these would be an sp3d2 orbital. And we'd have 6 of them. Okay, so sulfur would have 1, 2, 3, 4, 5, 6 electrons. There's no formal charges here. And then the fluorines would come in and bond here. Now we can fit 6 fluorines around here. Why? To maximize bonding. The more bonds we can form, the more stable. And so this is drawing the hard to follow because the fluorines are all sp3. Shouldn't have drawn this label there. This is up the fluorines. Something like this, etc. Drawing all the sp3 orbitals on the fluorine becomes more difficult as we extend it out. But the Lewis structure is not. The Lewis structure we could draw 3-dimensionally, like this. This is called octahedral because if we connect all the fluorines with a line, it forms an octahedron, an 8-sided polygon. So it's octahedral because of this polygon that's formed. There's no axial and equatorial. All sites are the same. All sites have 4 90s and 1 180. Repulsion. So take the silver ball and see. No matter what stick you grab, it looks exactly the same. And you could build this using the silver ball. Okay.